The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to today's webinar, Off-Grid Masterclass Part 2. Sorry about being logged out of the webinar a few times there. We had some technical difficulties, but everything should run smoothly from here on out. It was just a user login error running multiple webinars at once kind of thing. All right, welcome back. This is Part 2. If you weren't here yesterday, certainly welcome to this session. Before we jump into the content, I do just have those notes to go over like I did in the first session here. First, as a means of proof attendance in the event that either you or Half Moon Education is audited by any licensing boards, please be sure you're logged into the webinar using your own individual internet connection. As an extension of reporting accurate attendance, there's going to be a brief quiz at the conclusion of today's webinar. It's short, it's brief, it's just, again, meant to prove attendance. If you have any problems with it, call into our office or reply back to any of the emails we sent you. We can help you out with that. Attached to that email is an evaluation form. We do appreciate any feedback you can provide to us regarding our webinar formats and content and whatnot. So please take the time and fill out the evaluation to the best of your ability. We do appreciate it. Your certificates, you'll be issued one for each individual session you attend with us. So if you attended both Part 1 and Part 2, you'll get 2 PDFs emailed to you. They take about 5 to 7 business days to get to you, barring that we do have a quiz returned. We'll be taking questions throughout today. Anytime you have a question in regards to the content or for Half Moon Education, type them into the questions box that's on the right-hand side of your screen. Below that questions box is the handouts box. I have uploaded today's handouts to that area. We normally email them out, but we were receiving a lot of notifications that this attachment was too large and we couldn't do that. So I do apologize for not getting to you earlier, but it is the same one as yesterday. So if you already have that one, you already have today's. Okay, well, that's all I have. So now let's hand things back to Mr. John Ross Cromer, who's a master electrician with a mechanical engineering degree from the University of Pennsylvania. Thank you.
All right. Welcome back, everyone. Let's dive right in. Although, if you do have questions relating to the quiz questions from yesterday, feel free to type those in, and I will get to them as we move along in class. So one kind of key point from yesterday that we really didn't cover was talking about the implications of these cycle charts with lead acid batteries. And so what I would say is, you have in say a grid connected battery, you are trying to every day discharge the battery and charge it back up again. I know, some go with a very tiny battery just to turn the array on during a blackout, but that's a nice theory. It doesn't really work in practice. And really, a grid tied battery you want to put to use, even if it's somewhat spiteful in terms of discharging and recharging. With an off grid battery, you're usually operating in the top range of the battery and only getting down into the bottom range on those kind of once a year, twice a year storm cycles. And what that also means is you are going to be oversizing the battery a little bit. And the point I wanted to make, which I don't think we really touched on yesterday, is if, say, you go for an average daily discharge of, say, 40%. All right. And that'll give you maybe, let's just call it 1,300 cycles. And instead you oversize the battery and you hit a average daily discharge of 35%, what that means is you're going to get a longer life. You're going to get more cycles out of the battery. So, when we talk about oversizing with batteries, erring on the side of caution is not really going to waste your money, in the sense that if you err and you oversize the battery bank, you get a longer life out of it. If I put if I put too much inverter capacity and I only have a small solar array or a small load, I've spent more money on my inverter than I have to. I don't get a real benefit out of it. But if I overspend on my battery in terms of capacity, it just means it's going to last longer. Okay, so when you get to wiring battery systems, the wiring of the system kind of greatly it's a lot more complicated than a basic solar array. Now, for grid-tied commercial batteries, the solar guys say, oh, well, it is simpler to just wire up a $50,000 battery bank as opposed to a $50,000 solar array. What I would say is there are certain off-grid inverters that have a lot of this switchgear stuff already built into it. So say, for example, a one-way grid assist inverter that is not capable of outflowing onto the grid. So whether it comes from a generator or it comes from the grid, there's a transfer switch already inside an off-grid inverter that says we're either going to be flowing through the grid or flowing through the generator. Or sometimes it's either we're going to be using the grid to charge the battery or we're going to be using the grid to bypass the system altogether. Whereas, and this is just using one inverter for the entire system. Other kinds of battery inverters are what's called stackable. And so here's inverter 1 and here's battery inverter 2. And what you can see from this line diagram is the outputs of the inverter. I think this is the output here is coming and landing in parallel on an AC bus bar, and that the generator is also being wired in parallel. And so that would be the difference between, say, and then the AC bus bar goes and it feeds the load of the house. And so, in this configuration on the right, the generator and the batteries can run at the same time, whereas this this on the left, it's more of gets you closer to like an either or situation. Now, there may be a transfer switch here that's inside the battery inverter, but the local jurisdiction may want to see something that's external to the inverter. They might say, oh, well, the grid's going into that inverter, and so if you want this to be considered not grid interconnected, you're going to have to put the transfer switch on the outside of the inverter rather than the inside of the inverter. And then you're spending almost as much money on an external transfer switch as you are on these battery inverters that already have that switching functionality built into it. So, that's where I'm saying is you might run into some instances where you get the disconnects and the transfer switches built into your battery inverter, but your local jurisdiction might have some other interpretations on some additional balance of system material you need to get. That gets into kind of a downside of staying grid connected. This is I very much like this system. It's made by Schneider, and whereas my cheap Chinese inverter that I also use pretty frequently is not stackable. You can't have them wired in parallel to each other. Schneider's is, and that allows you to up the power output of the system. My cheap Chinese inverter kind of maxes out at a 12 kilowatt continuous output. And so if I was in a like 6,000 square foot home, 12 kilowatts continuous output may not do. It's the cost of this extra panel and the cost of these specialty breakers. And what we're looking at on this panel on the right is actually both an AC and a DC panel where the DC side is at the bottom, and these are all DC breakers, and the AC side's at the top, and it makes things kind of nice and neat and integrated. But it's, you know, when you do your cost analysis, it's not just the cost of the inverter, it's also the cost of not only the specialty AC and DC panel, but also the cost of these specialty DC high amperage breakers, which you just can't go into Lowe's and grab off the shelf, because there aren't that many readily available DC appliances. And so that's where I see kind of when you go for an inverter that is listed for grid connection, and not only for being charged from the grid, but also outflowing onto the grid, they're generally smaller than what it takes to power an entire house. And so then you want to get two of them and have, hey, there's nothing wrong with two inverters. It's doubly redundant. So if one fails, you know, you have the other one there to operate while you fix the first effective inverter. So it's not that there's anything wrong with double redundancy. In fact, a lot of people prefer double redundancy. But just keep in mind, it's not just the cost of the inverter, it's the cost of the balance of system material that really gets by the time you buy one inverter shell and then another inverter shell so that you can do whole house power and not just a critical load or a small amount of power. And then you buy the switch gear that's required to run both inverters in parallel with each other. That's when the cost of these grid-tied battery inverter systems really starts running away with you. Whereas if you're doing an off-grid cabinet in the woods, getting one cabinet that has all the disconnects and transfer switches between either charging with the grid or charging with the generator built into it becomes a little bit more cost. That's how you get that lower price point. So we have people are asking, what does AHJ mean? So this is basically your local permitting office or your local inspector office, where you know, that's one thing where in my territory, having an interconnected solar array gets you into a special additional solar meter fee. We saw that example yesterday where kind of the most egregious example is they add an additional $15 a month to your bill because you have an interconnected solar array. You know, it's this particular battery inverter can be charged from the grid. And even if it is just a one-way inverter, your AHJ may have their own opinion on what a grid-tied solar array is, and that could be a reason to go off-grid. So AHJ is your local permit office, your authority having jurisdiction over the array, and they're allowed to make up their own rules that go above and beyond National Electric Code. And often, you know, a good example where I commonly disagree with AHJ regulations is the need for an external, readily accessible knife switch disconnect. And so technically, the disconnect switch that your inverter lands on, that can be a readily accessible disconnect as required by National Electric Code to de-energize the battery inverter from the home or from the grid. A lot of jurisdictions will require you to put an additional knife switch disconnect that's readily accessible between the generator and the grid. The idea being that, I don't know, they want the ability, really what they want is the ability to walk up to the side of the house and throw a knife switch to turn the solar array off. And the reason why I don't like these knife switch disconnects, and the reason why they're not part of National Electric Code, and the reason why many jurisdictions have moved away from requiring the knife switch disconnects, is because you got the grid coming on top and the load coming from the bottom. You switch this disconnect switch off, and it still doesn't kill the grid coming in from the top, and yet it's a readily accessible requirement, which means that anyone can walk up to that disconnect switch, turn it off, open it up, and stick their hand inside and electrocute themselves because they don't understand that the top of the disconnect switch, just like the top of a utility meter base, could still be hot when the when the system is de-energized. So in other words, be very careful when your local jurisdiction requires things that go above and beyond National Electric Code, because while National Electric Code is a bare minimum standard for safety code, the rules that are added to it by local jurisdictions often can be like copying bad homework rather than actually being more robust safety requirements. So looking at, say, the cost of a large, actually, I went through the grid distributor process. This is more like, well, anyway, this is a 12 kilowatt battery inverter that is only ETL listed and not UL listed. So sometimes jurisdictions require not just listed components, but American UL listed components, whereas ETL is more of a European listing standard. And so that might not meet the AHJ requirements, especially if you're trying to argue that it's not a grid-connected array and that the transfer switch inside the inverter that allows it to charge from the grid but not output to the grid, that or bypass the system. That your AHJ may say, oh well, we still are going to consider that to be a grid-connected solar array, even if it's a one-way inverter. And there's also no double redundancy, whereas if something goes wrong in, say, the AC output of the inverter block, then you might have a power down for the whole system. Whereas if you had double redundancy, the system would be able to limp along at half power without completely being out of power. And that's something you have to think about as a designer. Is a lot of I have a lot of customers who want to go off grid to increase grid reliability, but if that means you're selling them the system, and if your system fails and they don't have any power, they're going to be looking at you as saying you increased the unreliability of my electricity. And so having two double stacked inverters next to each other could be a better safety practice. Well, two smaller things generally are going to cost more money than one larger thing. And then you have to buy that specialty distribution panel. And so you just end up getting, and actually this, I went and did better pricing after I made this. I made the presentation and then I started to do off-grid after the fact. And really this 12 kilowatt inverter is around 3,700 rather than 5,100. So I was looking at an Australian inverter, I think, when I did that pricing, and then I switched over to a Chinese inverter. And so you're looking at, for your kind of electrical system, going for that UL listing, going for double redundancy, going for an inverter that's listed for outflow and selling back to the grid. You could be looking at maybe twice as much in your inverter budget and associated balance of system material as you would sticking with an off-grid inverter. Not one that's unlisted entirely, but I'd say the off-grid market is still kind of small in the US, and so not, generally the companies that are selling off-grid inverters are also going through the UL process and listing them for grid connection. And what that means is there's going to be more safety provisions built into a proper grid tie battery inverter that you just would not use for off-grid, such as your grid tie inverter needs to detect when there's a power failure from the grid and limit its outflow. That's just an issue you don't have when you go with a off-grid, truly off-grid inverter. And so kind of going back to arguments against the grid, sometimes the balance of system cost and then the additional fees that are levied by the utility that may not, the solar sales rep may not be telling you that the utility is going to increase your monthly meter fee because you're a solar customer. And we saw that one example yesterday where, not only are they charging you more per month, but they're also taking some money out of what they say they're going to pay you, because technically, even with PURPA, which is a federal mandate that says if you're a renewable generator, the utility has to buy your outflow at their avoided cost of doing business. In other words, there's a federal law, and there are very few federal regulations of the price of electricity. That's generally left to the states. But there is a federal law that says, well, if it's a 100% green generator and it is producing outflow onto the grid, the power company has to buy it at the raw material cost of coal. And say, don't buy raw material coal, buy this refined green electricity at the same price point. Well, technically the law says you have to buy at avoided cost less an administrative fee. And so a cooperative can press that administrative fee to be $15 a month plus a wheeling charge for any kilowatt hour output. That makes that PURPA mandate watered down so that the utility technically can buy the electricity at less than their avoided cost of raw material fossil fuels. And so either that, or maybe the permit office is so jammed up and you can't get electrical inspections. I know at least back in the day, the city of Austin, they would have tons of electrical inspectors, but they'd only have one solar inspector. And so getting all your inspections through and the utility approvals, that is what takes the bulk majority time of the installation. And, customers want their projects now. So, maybe an off-grid project, the logistics are easier to implement. Or the cost of grid expansion is another major driver. So we're going to look at some, what is the minimum you can do? If you have a grid tie inverter, what's the minimum amount of batteries you have to add on it? This is a Schneider battery inverter. And so, the minimum battery kind of depends on your battery voltage. So there's not just amp hours, but also volts. Volts equals, or power equals volts times amps. Energy is power times time. So the energy component is this hour. And so what we'll find out is these components can operate at multiple voltage settings. And so this Schneider inverter can accept a 24-volt battery bank, or it could accept a 48-volt battery bank. And so the minimum size battery that you can do on the Schneider system is 440 amp hours. And so if you wired a 24-volt, 440 amp hour, that's about 10 kilowatt hours of flooded lead acid. And so I think that's kind of interesting in the sense of if you're on the fence between doing a grid tie inverter that doesn't have batteries and one that does, if we're looking at 10 kilowatt hours of industrial flooded lead acid costing about $200 a kilowatt hour new, then you're looking at an added cost of about $2,000 in batteries. And then the battery inverter itself is more expensive than its batteryless counterpart. And so you'd be looking at maybe a minimum cost of adding $4,000 or $5,000 to your contract in order to get a small battery added to the system. Now, you could not use this 10 kilowatt hour battery all at once. You know, what it's really there for is to turn the battery inverter on during the day and allow the solar array to be on with the battery inverter so that you can use your energy during the day and then, you know, hunker down at night. You know, most homes use around 30 kilowatt hours a day or more. And so a 10 kilowatt hour battery bank is only going to be, you know, maybe 25% of your daily energy use. So, you know, that's having a small battery doesn't give you whole house backup power. Instead, they relegate it to kind of minimum loads. There's a battery design concept called DC coupling, and it's compared to its AC counterpart. Basically, what it means is on a DC coupled array versus an AC coupled array, it's how does the solar array interact with the batteries. So on a DC coupled array, the solar array is hardwired to the batteries, and then the batteries through the inverter go into the load. Whereas on an AC coupled array, the solar array is separate from the battery bank, and they're both wired into the AC service panel. Well, what are the differences between them? You know, which is better, AC coupling or DC coupling? Well, in DC coupling, the energy is going to be processed from the array through not an inverter, but a DC to DC conversion process called a charge controller. And then it's going to be processed out of the inverter into the load. So that's a 1-2-step process. And there's a little bit of an efficiency loss here. There's a little bit of an efficiency loss here. Now in AC coupling, you know, let's just say this says loads, let's say, or grid. In AC coupling, to get from solar to the load or the grid, you're only going through this one-step process with a little bit of efficiency loss. And so if the goal is to power your home with solar during the day and any surplus sell it back to the grid, AC coupling is going to be a little bit more efficient. For that matter, you may not really be using the batteries. The batteries, if you have a good sellback rate to the grid, the batteries will just be hanging out and you'll be selling back to the grid. Whereas if you're using the batteries on a regular basis by charging them and discharging them, under AC coupling, you would have to charge them, that's step 2, with a little bit of efficiency loss, and then discharge them, that's step 3, with a little bit of efficiency loss. And so if you're living off grid, where the goal is, yeah, you're using your batteries most of the day, DC coupling is going to be a little bit more efficient than AC coupling. There's also an issue of voltage to consider. I think we'll talk about that a little bit later. But this is where the lithium-ion systems get to be a little bit more efficient, because we have to remember the solar array is done at 600 volts typically. And if I have a 48-volt battery bank, there's the efficiency loss in getting from 600 volts down to 48. and then I'm going back up to 120, 240. So I'm going back up again, and there's a little bit of efficiency loss there. What a lithium ion system will do is it'll take the 600 volts, and then the battery bank instead will be 350 volts, and then your load will be 240 volts. And so the energy is like a boulder rolling down a mountain. It'll go from its high potential to its low potential. And so if that boulder has to go all the way down the mountain and then down into the valley and then back up the mountaintop, that's going to be a lot less efficient than it just kind of rolling, straight down. In this case, the coefficient of friction being your electron efficiency loss. The main advantage of DC coupling is that when the sun comes up, it turns your solar array on, and then the electricity flows out the charge controller into the battery. Under an AC coupled system, let's say it's cloudy and your solar array is no longer working. So now your solar array is no longer working, and now you're running off your batteries in an off-grid setting, and let's say you fully deplete your batteries, and then the sun comes back up. Well, you have to remember in AC coupling, these are inverters, and commonly they are grid-tied UL-listed inverters, which means they have to see a signal from the grid in order to turn on. And so if your battery bank is fully depleted and the sun comes back up and you're fully off grid, your solar array will not turn on because it doesn't see any signal. Now, that point is more theoretical than anything. In reality, either you're going to have a little bit of reserve capacity left in your batteries to be able to turn on when the sun comes back up, or you're going to have a generator there playing free safety, and that'll be able to crank the system and get started. Generators kind of have a similar issue where there's a battery inside the generator to power that electric start button on the generator. So, and then if that battery drains, your generator the electric start won't work, and you might have to hand crank it. So, this is not just a solar issue, but you'll see some discussion of, in AC coupling, the system won't be able to black start. Whereas in DC coupling, you don't have that issue. As soon as the sun comes up, the batteries start to recharge. And so maybe there are a few more technical merits of DC coupling. Another technical merit of DC coupling is going from a high DC voltage to a low DC voltage is less costly than going from a high DC voltage to a low AC voltage and having it be a full-blown inverter. And so technically speaking, DC coupling should be cheaper than AC coupling. But the thing is, the AC coupled market, solar going straight into an inverter without any batteries in between, that's been the solar market for the last 20 years. Maybe 10 years. Maybe it's not been that big of a market. Well, that's been where all the solar growth has been. You see any solar articles, they're all talking about grid-tied solar, batteryless solar, and that means these solar inverters have achieved manufacturing economies of scale such that they've become very cheap. And your DC charge controllers have not had the same kind of attention. And so from a cost perspective, DC coupling versus AC coupling is DC should be cheaper, but right now it's really not. Your high-end charge controllers cost pretty much the same as your standard no-frills DC to AC inverters. you might have the solar array be very far away from the battery bank. Or you might have the solar array already on site and you just want to add on the battery bank. And so that's when you'll be faced with, oh, do I do a DC coupling or an AC coupling situation? And really, I think at this point, because the cost of the charge controller is about the same as a batteryless inverter, because there are remedies to overcome the black start issue, whether it be reserve capacity in the battery or adding on a generator to crank, there's just not that much of a difference between DC and AC. DC coupling will win the theoretical, technical discussions, and as the industry moves forward, we should see DC coupling become more of the standard practice. But right now, there's more opportunity for retrofitting existing solar arrays with batteries than there is selling new solar arrays with batteries. And there's nothing wrong with AC coupling. In fact, it's the preferred method for commercial systems and utility systems because for two reasons. One, it's grid tied, so most of your solar production is just going to dump directly into the load or the grid. And two, the high-end commercial and battery inverters come with their own dedicated inverter, much like the Tesla Powerwall. And so just clicking it onto the existing AC service panel is usually will result in the easiest install. And so I would not get, and the fact is you could do both. You could have an AC coupled solar array on AC coupled to a battery bank and still have a little bit of solar that's DC coupled to that battery bank on a small charge controller in order to overcome that black start issue. And you can always add a generator onto it. Now, charge controllers, I mean, it used to be that back in the 80s and 90s, maybe even before then, every solar array had a charge controller because it was an off-grid market. Then we went through the last 10 years has been a revolution in solar for grid-tied solar. And so all your old solar pros will have plenty of experience and recommendations on their favorite charge controllers. And a lot of the new guys in solar don't even have a clue about where to begin with charge controllers. Now, you can find little cheapo $30 charge controllers for a single solar panel, which are kind of neat. They have their uses. Solar Edge puts a DC to DC voltage regulator behind every panel, even if it's a batteryless system. And to some extent, that is a charge controller. They call it a DC optimizer, but it is a voltage regulator. It's a synonym of a charge controller. A lot of these charge controllers come from the same roots. And so Schneider bought a company called Xantrex that bought a company called Trace Inverters. And both Outback and Midnight and Magnum all come from that same Trace Inverters company of yore. Whether they be spin-offs or engineers quitting their jobs to form their own companies, and you can kind of tell some visual similarities, say, between Outback and Midnight. And I would say Outback and Midnight in the United States have the best reputation among installers. I have my own opinion. I have no doubt of the quality of Midnight or the quality of Outback. The problem I have with Midnight and Outback is that their charge controllers are mostly 150 volts, maybe up to 300 volts. Whereas I prefer Schneider, and the reason is it's a 600 volt charge controller. Well, what does that mean? We're going to get into it in a minute. Victron is very popular in Australia. Magnum is a good kind of budget version of Outback. Midnight is generally considered a little bit more high-end than Outback. And then there's TriStar, which is another 600 volt charge controller worth considering. I just don't have any direct experience with them, so I can't really say, vouch for their quality. But I would put them in the same kind of category as Schneider, except they're a smaller company. So back on that, choosing between a 600 volt charge controller or a 150 volt charge controller, remember the charge controller goes between the solar array and the battery bank. And when I'm doing just regular batteryless solar, I'm going on up and designing around a 600 volt circuit. Well, if I have a 600 volt circuit and I try and wire it to a 150 volt charge controller, I'm going to burn up my charge controller. It's not going to work. And so if I have a 150 volt charge controller, what that means is I can't do 600 volt circuits. I'd have to do 150 volt circuits. And so what that means is normally on a 600 volt circuit, you're going to go up to 9, 10, or 11 solar panels. On a 150 volt circuit, you may only have 2 or 3 solar panels. And so if I'm doing a 50 panel system, my choices, I could either have 6 circuits on my system, or I could have 18 circuits on my system. And especially if I'm on the rooftop, or if I'm doing a ground mount that's far away from my battery bank, I'm not going to wire 18 circuits up to my rooftop. I'm not going to wire 18 circuits through the ground when I could cut that number by 30, by 1/3. And so that's kind of where I come in on, being a big fan of 600 volt charge controllers, is because I like the DC to DC connection. I like doing DC coupling for black starting, not needing the inverter, not needing to worry about reserve capacity in the battery, having it there so that if the client actually bricks their battery, when the sun comes back up, they'll start producing power again. If I'm doing a ground mount that's right next to my house, maybe wiring up all those circuits is not a big deal. I would rather avoid it. So, I kind of limit my own charge controller selections by going with 600 volts. Another problem we run into is these specialty breakers, because when you go with a charge controller that has high voltage and low amperage coming from the solar array, but then it hits a 48 volt battery bank that's going to be low voltage, and it's the same amount of power going into it, your conversion has traded high voltage and low amperage for low voltage and high amperage. And that means the charge controllers, before they go into the battery bank, they're going to have to land on a high amperage DC breaker. Well, Schneider sells one high amperage DC breaker for $100. I had 3 of them on my last job site. You know, if you have 150 volt charge controllers, you know, you're buying a lot more breakers too. You know, that's kind of where your balance of system costs can start running away from you. Now, what I did, I actually on my first design, I ordered my breakers in a rush, and I looked at the output amperage of my Schneider, and it said 80 amps. And so I thought, oh, okay, well, this isn't my main overcurrent protection device for the system. I'm just going to get an 80 amp breaker and land on it. Well, the problem is I generally oversize my systems, and I was actually getting all 80 amps out of that charge controller, and it was tripping my breakers. I really should have done it properly and upsized the breaker with a 100 amp breaker. You know, it was just one of those things where, oh, we're doing the project, we need the breakers, it's 80 amps, call up, order an 80 amp breaker, forgot to upsize. Well, then the breakers started tripping. I was like, well, I need to fix it. Man, buying $300 breakers is not something I want to do. Well, what I did is I went and I looked at the original equipment manufacturer of the DC breaker and typed that into eBay and found that it's not Schneider making these breakers. And I was actually able to find a 3 single pole breaker pack for less than $50 total. It's literally the exact same breaker that Schneider was selling for $100 a pop. So, you know, high amperage DC breakers are not so uncommon that you can't find them online. It's just that if you buy them from your solar distributor, that's where, you know, they're trying to make their profit, is in these, you know, they can give you a lower price on the charge controller, knowing that you're going to have to turn around and buy their high markup breaker. But they needn't be so expensive, is what I'm saying. So there's a inverter startup in Portland, Maine called Pika, Pika, and they kind of, the reason why I think they're worthy of note in this program is they've kind of smartly combined the best of all worlds. First off, they put little boxes behind their modules to optimize the voltage coming out of it. But unlike SolarEdge that does one box behind every single panel, Pika does one box just for the circuit, and it optimizes the voltage of the circuit. And so it's a little bit cheaper than the SolarEdge system up on the rooftop, but you still get a steady voltage coming out of the array. And what that means is your inverter costs can go down a little bit, because instead of being fed a variable voltage that spikes up and down, etc., the inverter is being fed a constant voltage with variable amperage. And it's a little bit cheaper to control your equipment costs with a constant voltage rather than a spiky voltage. And so they're regulating the output of this home run circuit and kind of keeping it at a steady 380 volts. And they say, okay, well, your circuits, we're not going to have 10 or 11 panels per circuit. We're going to string up enough panels to get us to about 380 volts. And so they're really taking the operating voltage of the panel, which might be between 360 and 400 volts, and just keeping it at 380. Whereas SolarEdge is going from a single 30 to 40 volt panel and stepping that up to as much as 600 volts. the Pica optimizer is already starting at that higher voltage, so it's not doing quite as much processing. So technically, it could be a little cheaper, although it's not because they're a smaller company, and so you're only buying one of them rather than 6 of them or one per module. So another thing they've done is gotten with a flooded lead acid battery manufacturer and developed a high voltage flooded lead acid battery, which is cheaper than buying a high voltage lithium ion battery. I actually don't think they're doing it quite right because they're going with a sealed AGM flooded lead acid. Although I've talked with my preferred forklift manufacturer, and they don't really see any reason why you couldn't string up their batteries into much higher voltages. And so what they've done is they've put their battery on a battery management system that also keeps that battery output voltage compatible with this 380 volt bus and landed it on an inverter. So it's kind of like a solar edge system, except you can just click on additional batteries however you see fit and run the load. And so I kind of like them because they got one optimizer for the circuit rather than for the modules, but they also have the option between flooded lead acid or a lithium ion battery, and then they have a inverter that's designed for the optimizers, which is a little bit cheaper than one that can take variable voltage. Now what I would say is even though technically their cost should be optimal, the size of the company means that it's not. They're a startup, whereas others are not in there. Well, Jerry says, where in the presentation is this page? This might be a slide that I had stuck into it at the end. So just look up Pica if you're interested. Well, probably one of the larger issues I have with doing off-grid flooded lead acid batteries is where do you put them? Because they take up a lot of room. Solar is electrical equipment, and electrical space has to be dedicated for electrical space. So you can't have actually. So this is Half Moon's electrical room, and they went up this air conditioning duct is right at the bare minimum of the reserved vertical space for your working space for electrical. So even your air conditioning ducts can't cross into your electrical space. You're not supposed to have gas lines and water lines running in front of your dedicated electrical space. This is low voltage stuff, so it's not technically going to be in like your fiber optic is usually different and not considered electrical like proper power lines. And so the key point here is your space for your inverter, your space for your batteries. It has to be just electrical space. And so, we have often homes will have a closet for their tank water heater. Now you have to have a room for your battery equipment, electrical equipment, and it takes up more space than a dedicated space than a tank water heater. Now, these spaces can be adjacent to each other. It's more just like a invisible fence that you can't pass over. The idea being that the worker, the electrician, can do all his job in front of the electrical work without violating any crossing over into any other scope like gas or plumbing. Another thing is the rooms have to be vented. You know, your unsealed flooded lead acid will emit gas, particularly when it's being used and charged. And that gas is explosive. So it needs to be kept to less than a 3% air quality concentration. And so your space has to be vented. And there's actually two different definitions between international residential code and national fire code. And the main difference is that in international fire code, the ventilation of these unsealed flooded lead acid batteries, it has to be continuous ventilation, like a computer fan inside your computer. And so what that means is a lot of it used to be not an IFC when you don't have this continuous ventilation. It's just, you could have a fan click on and click off to make sure that the gas in the room, the hydrogen gas, is less than 1% of the volume of the room. Then IFC came back in and said, well, actually, we want to make sure that you're not trying to push the limit. We want you to continuously vent. And so that has led to the concept of a sealed battery cabinet, where it's just the container that the battery is in that gets continuous ventilation, rather than the whole room that might have a fan clicking on and off like an air handling unit. Technically, an air-conditioned room is a ventilated room. And so IFC is saying you have to do a little bit more than just put your unsealed lead acid batteries in a air-conditioned room and say that because you have air handling units inside the room, it's ventilated. And then I added in some additional, another aspect is the rooms have to be locked to prevent access to unauthorized personnel. Whereas U.S. National Fire Code, the big difference between us and International Fire Code is it's a either-or situation. It's one of the following, not both. Now this gas is mostly hydrogen. It's lightweight, and so it'll go up to the top of the room. And so putting a hood over the batteries and venting that hood vertically to the outside, should alleviate the safety danger. So, having a hood over the batteries that gives the lightweight gas the ability to vent to the outside on its own, but putting a small fan inside the tube to turn on when the battery is under heavy use, or you're going through your maintenance charges by pushing that battery all the way up to the very top of its voltage. Ventilating during those times is the way to go. And then consider to have the highest stringent safety considerations, what is standard in international fire code but not part of national fire code, would be to fully enclose the batteries in a cabinet and then have a small fan running continuously inside that cabinet. Um, UPS is a uninterrupted power supply. I forget which there it is. And then VRLA is valve regulated lead acid, which is almost like they put it's an unsealed lead acid, but they put a cap over the top of it, which basically its goal is to prevent water vapor coming out of the batteries and let that drip back down into the batteries. So a valve regulated lead acid battery is not like a sealed lead acid battery, but it requires less watering and maintenance than an unsealed lead acid. And so it's a little bit of a kind of the next step up in lead acid cost. There are additional requirements for battery rooms in areas where children are located. Um, this is one that's kind of interesting. If your battery banks get sufficiently large so that you can fit more than 1,000 gallons of water into your battery, then you have to implement spill control. Now, I haven't come into residential systems that large. So then we get into temperature control. And this is a little bit more controversial because lead acid can take a wider temperature range than lithium ion. You know, I delivered some batteries to site in Mississippi the other day, and it started to dip below freezing. We hadn't turned the system on yet, didn't have our heaters running yet. So the question is, are the batteries going to freeze? Well, the electrolyte inside the battery is a little bit like salt water, where they're not going to freeze at 32. It's more like they're going to start freezing around 14 or 15 degrees Fahrenheit. And then unlike lithium ion, which has severe temperature issues, you know, lead acid can take a little bit of a higher temperature. So you get higher operating temperatures, you get a wider operating temperature range with lead acid, but that doesn't mean it's that regulating the temperature of the battery isn't a bad idea. In fact, here's like the Schneider inverter, and what you can see is once the temperature gets above 80 degrees, the efficiency of the system begins to drop. And so it is a good idea to air condition your inverters. You know, it's not that you have to, it's that their efficiency improves if they're kept cool. Their life improves if they're kept cool. You know, same thing with your batteries. You know, I've read about batteries sitting on freezing cold slabs, and the temperature differential, and that causes a temperature differential across the bottom to the top of the battery, and that can lead to early cell degradation. So, you know, I think that it's just wise to provide as much temperature regulation as you can, not because of necessity, but because of performance. And so what we see in battery spec sheets is here's freezing point right here. What we're seeing is your your flooded lead acid can actually get below freezing, below 32. Can even get much below 32. So here's the battery being rated down to negative 20 before it starts freezing, with the caveat of when you get into those negative temperatures, talking Fahrenheit here, you have to keep the battery at least 50% charged. So, they're up there having a blizzard today in Wisconsin. You put your batteries in a battery box outside. It can get into negative temperature weather without freezing the battery, as long as you keep the battery charged. Now, I think it would be better to have a battery box that has thermal mass in it so that you can heat the thermal mass up a little bit during sunnier weather, and then try and keep that battery box from dipping below zero even when it's below zero outside. Now, also what we see is batteries will actually be able to store a little bit more power at higher temperatures. But when they operate at higher temperatures, they're going to get fewer cycles out of them. And so this graph on the right is more pertinent to lithium-ion batteries. But basically, what it says is, you might get a lithium-ion battery that says it can go outside on the wall, but if it's operating in a hot Texas summer weather, and you have to keep in mind it's not just going to be what the temperature is outside, but the temperature outside is going to limit how much temperature internally that the battery inverters can wick off. One of the problems with the Nissan Leaf was that they didn't put temperature regulation into the battery compartment, saying, oh, well, the batteries, will continue to operate at higher elevated temperatures. Tesla, on the other hand, puts temperature regulation into their batteries. So, I don't know. I think it's a good idea for a variety of reasons to stick a portable air conditioner unit inside the battery room to provide air ventilation, to generate water, to provide some heating and cooling, and maintain the temperatures of the batteries. And the benefit of that is it's more controlled. And so, as I was saying yesterday, I've been able to go to my battery manufacturer and get permission to not open up the batteries every 2 weeks to measure the specific gravity of the cell as their warranty guidelines state, because I am doing the temperature regulation and current monitoring. So actually, these rooms still have electric code violations in them. You are going to have to take as part of your maintenance, you're going to have to measure the specific gravity of each battery. Now, most of these batteries are going to have multiple cells in them, and so the procedure would be to just measure one cell per battery. But the maintenance procedure would be to come in, unscrew one of these battery caps, stick your hydrometer down it, and do that for every single battery along here. Now, it may be something that can be done in 15 minutes, but how are you going to take the specific gravity reading of this battery in the back? You can't access it. You have to lean over the battery bank. And so if you have a particularly fastidious inspector, he'd say, no, this is, if you have to maintain that little bit, you got the electric code clearance requirements to consider, which is, maybe you can put it 30 inches of clearance, and that can start at the side of the device. But then there's another National Electric Code rule. So you got like the width of about 30 inches, the height of about 6.5 feet, the depth, which is if I'm standing in front of the equipment, it's usually about 3.5 feet from the faceplate of the equipment to behind me. But then the last one is another depth issue, which is how far in front certain electrical components can stick out from each other. So, for example, here we have our inverter equipment and our batteries sharing the same wall, kind of like they do in this picture here. Well, you can only have equipment sticking out no more than 6 inches from the front of this to the next piece of equipment. So, you might have your electric service panel here and your solar inverter here on the same wall, and that's fine as long as there's no more than 6 inches in depth difference between them. Well, actually, it would be fine either way because they're to the right or to the left of each other. But let's say I wanted to put this electric service panel underneath here. And so we have one panel that's serviceable, another panel that's serviceable. You couldn't have more than 6 inches of depth. And so the problem is now we have these batteries sitting in front of this service panel, and even though it's dedicated electrical space, there's 30 inches of batteries sticking out in front of this service panel. And so that would be a code violation. For that matter, they've made this little terminal, not particularly accessible. Now, whether an inspector would disqualify you or not, I don't know, but the point is you can't just shove the batteries up against a wall. A better layout for this battery bank would be to rotate it 90 degrees and have that part of the battery against the wall and then have the battery rack come out from the wall so that you could actually go and service each terminal of the battery. And what that implies is you can't just put the battery up against the wall. What at minimum, you're going to want to be able to walk around the battery in order to service it. And so it's probably better if your battery has a long end and a short end to put the short end against the wall and have the battery stick out rather than the long end against the wall, simply because your inspector might say, look, it's more than 6 inches to get to this back cell here, and so you're going to have to access that cell somehow. In order to do it as you currently have it laid out, you're going to have to lean over the battery bank to service that. And what happens if you have a wrench and you drop it into the battery and it connects 2 terminals together? That's the safety code says don't set your client up to maintain a battery in that manner. And so these battery rooms actually do take up a lot of space. Just remember, you're going to have to be accessing them. Furthermore, especially if you're going into double redundant systems with multiple charge controllers, just keep in mind that not only do you have to have space for your solar inverter or charge controller, but then you also have to have the space for your battery inverter. I don't think we really kind of got into the nuance between the difference between a solar inverter and a battery inverter. Let's remember that the solar inverter is one way. It's taking the solar array processing the electricity and dumping it into the load. This battery inverter is, or maybe not, maybe not this particular battery inverter. This battery inverter is two ways. It's going to charge the battery and it's going to discharge the battery. And so it's almost like two inverters instead of one. I have a weird kind of battery inverter that's a one-way battery inverter, and so I have to do DC coupling in order to charge the battery up, because the battery doesn't charge from the load. The generator would have to go on this side. But like your Outbacks, your Outback inverter, your Schneider inverter, your SMA inverter, your grid-tied battery inverters, they can charge from the grid, they can discharge into the grid. That's different than a solar inverter that is traditionally a one-way inverter. So your battery inverter is it's newer in the sense that it's had fewer design iterations. It's larger in the sense that there's more stuff inside of it. So it's going to take up more space than a traditional solar inverter. And so this space is almost good. If this were a sealed battery that did not require any maintenance, there would be nothing wrong with this room layout. But because you have to maintain that back, this whole layout might have been a little bit better if they had just put a little bit of a window here. Although I guess really accessing these would be hard. Maybe a pull-out tray where you can pull the batteries out, assuming you have enough slack in your battery cables to do so, which is what they do with forklift batteries. They put them on little trays that can come out from the underside of the forklift. So how large are these batteries? We used this battery for a off-grid project where we had 8 of them. And they're 38 inches long, 10 inches wide, 25 inches tall. And so, and these particular batteries weighed 1,000 pounds each. And so we went with this battery layout here, and in his garage, that's not a perfect code violation. And what he said, well, if it becomes a problem, he can put a little window access door into this sidewall so that he can access both the front of the battery and the back of the battery. Storage batteries and battery management equipment should be listed. That's not applicable to lead acid. What this really means is you can't professionally have a business where you're taking recycled lithium-ion batteries and putting them in from, like, say, wrecked Nissan Leafs and putting them into homes, because they're not listed for that purpose. So you might be able to find some used lithium-ion batteries online that are in the same price range as used lead acid. But if I put a refurbished lead acid battery into a home, I can still maintain code compliance. Part of that has to do with lead acid staying below 60 volts, whereas lithium-ion battery banks are high voltage, 380 volts. All right, so disconnects. A disconnecting means should be provided from all ungrounded conductors derived from stationary battery systems with voltages over 60 volts. Or, and this gets into disconnect requirements that are very similar to solar, you have to provide that external disconnect switch when it's not within line of sight of the point of interconnection. Similarly, you need to have a lockable disconnecting means when the disconnect switch is not within line of sight of the battery bank. There'll be a couple of more disconnect rules we'll get into. When the battery chemistry has a corrosive electrolyte, the support structure for the battery should be resistant to deterioration. Metallic structures shall be provided with non-conductive support members. Paint alone should not be considered an insulating material. And so what that means is I get a refurbished forklift battery, and it comes in a painted metal box. And obviously they don't want that metal box to be conductive from the battery. You know, you don't want to put that battery inside a forklift and touch the side of it and shock yourself. But what they're saying is you can't just put that box on the ground and say, oh, it's insulated from ground. What you need to do is take a rubber pad and put it underneath the battery before you set it down on concrete, because wet concrete can conduct electricity. Likewise, if you're putting your batteries onto a metal rack, you should put a rubber pad between the battery and the metal rack. Let's see. So then there's a section of National Electric Code that applies to battery banks that are over 60 volts, such as lithium-ion battery banks. What can get a little bit confusing is that a 48-volt battery bank will actually operate at 53 or 54 volts, not 48. And so the nominal voltage of a battery is like its nickname. So there is a voltage range that the battery is going to go in. When it is charged up to the very top, it's at high voltage. When it's discharged to the very bottom, it's at low voltage. When you go through a battery maintenance cycle where you're overcharging the battery to bust the barnacles off the top, you're charging it all the way up to its top rated voltage, maybe around 58 volts or so for a typical 48 volt battery bank. But you still refer to it as a 48 volt battery bank, even though it might be charged up to 48 to 58 volts, even though when it's fully charged in its float range, it'll be hovering around 54 volts. Even when it's discharging and getting down into its lower voltage, it'll still be above 48 volts. It's just 48 volts is kind of the nominal voltage or the nickname voltage of it. So there are additional requirements for higher voltage battery banks. National Electric Code likes to repeat itself a lot, so we see the ventilation requirements come back in. We see a working space of 1 inch between the cell and any wall or structure that does not require maintenance. So the batteries have to be 1 inch offset from the wall. Egress and illumination. So those are kind of interesting. When you're doing a lithium ion bank, you have to make sure your areas are illuminated. Also remember that National Electric Code requires us to put DC circuits run inside a building into metal conduit. I have not seen that requirement be applied to battery banks yet. Often like a forklift battery will have welding cable put into it, which is like a flexible plastic cable. I actually think that this metal conduit protection for PV systems is a bad part of code. People get the false impression that the metal is there for a grounding path, whereas really it's just there to provide additional protection, physical protection of the conductors from being hit by people. And so often, like in multi-story apartment complexes in New York City, or conduit that goes alongside of a driveway, a local jurisdiction will step in and say you got to use rigid conduit or intermediary conduit, which is a little bit thicker than standard conduit, to give it additional physical protection. But it's not something that has to do with DC specifically. So I haven't come across a call out that says your battery cables have to be in metal conduit. I've only seen that applied to the solar DC, but I'd expect that would come soon. Live parts of electrical equipment operating at 50 to 1,000 volts shall be guarded against accidental contact by having rooms that are accessible to only qualified people, by permanent partitions, by location. And so, the question is, well, can you just put a Tesla Powerwall, on the side of a room? Well, the Tesla Powerwall has an enclosure that completely surrounds the batteries. Well, is a garage only accessible to qualified persons? It might be better to put it into a locked cabinet or even a locked custom-built box inside of the garage. So this is additional requirements for, higher voltage battery banks, where energy storage systems are more than 5 feet from the connected equipment, or where it's could be less than 5 feet, but you're going through a wall. Maybe you have the batteries on one side and the inverter on the other. Then you need to have a disconnecting means at the end of the circuit, plus a second disconnecting means located at the equipment where the first disconnecting means is not within sight of the equipment. And so basically you have to have a disconnect switch whenever it goes through a wall, or whenever the battery is more than 5 feet away from your charge controller and from your inverter. And so what that means is you don't want to have, well, it's not that you can't have this stuff far away from each other, but you don't want to get excessively far away. So maybe the best battery layout for flooded lead acid is, again, where you have the short end up against the wall, but the long end sticking out from the wall so that you can actually go and service all these little terminals as needed. But then to keep your battery and your inverters within, or about 4 to 5 feet away from each other, so that you don't have to add the additional disconnect, but also that you have the 3.5 feet of working space to 4 feet of working space between your inverters and your batteries. Possibly, if your charge controller and your inverter and service panel are small enough, another good place to locate them would be right on the end right here on their own rack, kind of facing outwards. And so if you're designing a battery box to kind of maybe sit outside and you just want to put all of the equipment outside, what you'd be looking at is remember, these batteries are 10 inches each, and this is a 122 kilowatt hour battery bank, which is a little bit on the large side. Half of that, 60 kilowatt hours, would be only one of these things. But if you wanted to build an outdoor battery box and put all of your equipment in it, what you'd be looking at is maybe 4 feet for a large battery, or 8 feet for a or for 4 feet for a small battery and 8 feet for a large residential battery, and then giving yourself another foot to build and mount your inverter and charge controller equipment. And then I would say you would also want to leave a little bit of space somewhere, maybe additional space here for a water tank and a portable air conditioner equipment. And so your total battery room is going to need to have, I know I said 8 feet by 8 feet here, I would say 10 feet by 8 feet at minimum for your battery enclosure and associated equipment. Another thing you could do is build a liftable platform, and you go 6.5 feet up, put another platform there, and just keep your batteries kind of out of sight, out of mind, although they're very heavy. So, if you're an engineer, maybe that's something you can start doing, is putting kind of unistrut-based battery hoists in the garage so that you still have working space underneath, and put the batteries up above the rest of the system on a platform. Jerry said, how do you record amp hours consumed? And we're going to get to that point after the break. Another issue I found that can get ignored when you're doing an off-grid system is grounding. And the reason is, your home does not just have one ground rod. It also has a secondary ground rod. You just don't see it. And so typically you're going to have a ground rod, at the side of your house, and then often the utilities will have another ground rod that's grounding at the pole. And so the kind of good rule of thumb for your off-grid homes is just to remember to get 2 ground rods and put them in right next to each other. Here's the call out in code. A supplemental grounding electrode is required if you're using certain kinds of grounding electrodes. So often with solar, we're used to using a ground rod to ground our systems. Just remember that if you're building a whole off-grid home system from scratch, you're going to need a supplemental electrode as well. Here's another reason why a lot of battery inverters just have these small rink-a-dink critical load panels. So they do an automatic transfer, and code says if you're supplying an emergency system, which, hey, a lot of people who buy solar and batteries, they might have medical equipment that they want to work during a blackout. Well, not even emergency, just for optional standby systems. Life-saving equipment could have additional requirements. Says the automatic transfer equipment shall be capable of supplying the full connected load. And so that's where the solar battery grid tied companies will say we're only going to output 2 kilowatts of power on a critical load. They're not capable of supplying your whole house. Even if you had a 6 kilowatt inverter, battery inverter, that's generally not enough to supply a whole house. And so, we see that these kind of residentially sized battery inverters that are up to 6 or 7 kilowatts in size still don't provide whole house power during a blackout. And that's where I like getting into like 12 kilowatt systems with burst. So, in the interest of time, let's take our halfway break. Let's just take 10 minutes. So we'll pick back up at a quarter till. Let's take a 10-minute break and then continue on with our discussion. Realistically, we're probably not going to get into kind of my whimsical Franken-solar discussion. We'll probably spend more time on racking and generators. What this last part is how to kind of combine grid-tied lithium-ion critical load inverters with lead-acid baseload battery inverters so that you can kind of have your cake and eat it too. But I think we probably won't get there. So, let's take a 10-minute break, and then we'll pick back up at a quarter till. Wow. Well, that went fast. Welcome back, everyone. Um, let's see. Someone was mentioning misspelling. Yeah. Um, property is what it should be. So intended to supply power to public or private systems or property where life safety does not depend on the performance of the system. So yeah, that's just there's a difference between standby systems and true emergency systems in the eyes of National Electric Code. Okay, let's just recap some racking rules. One common racking mistake I see, especially in areas of heavy snow, is just doing a standard racking layout. Whereas it's a good idea even if you're going, your solar rack is often rated for a 6 foot span, but many pro installers will just go to a 4 foot span and make it a little bit more robust. I mean, you don't always get 2 foot on center rafters. Sometimes it's 16 inches on center, and so 4 foot is usually something that's going to lay out pretty well along the rooftop. Even so, I would recommend reinforcing the corners of the array. That's where you're going to get higher loads. And especially if you're in heavy snow areas, taking the bottom row of rail and going 2 foot on center across the bottom row of rail in particular, because that's where you're going to get snow, or at least the weight of the snow is going to most greatly impact that bottom row of rail. And otherwise, you kind of go for staggered L feet is like the tip of the top in terms of quality, so that you're hitting every single rafter as you go along, even though you have that 48-inch span. Last year, I took some jobs for a developer, and I was looking at his designs. And I thought this design was ugly, and we went with something a little bit more logical. But the designer he was using had a good point that I hadn't seen raised before about rainwater runoff of modules, where he had a tributary area call out in his designs. And that got me thinking, well, that's kind of true. Your 25-year shingle life is assuming that the rain is going to fall evenly across the rooftop, but aren't those shingles going to be degraded along the bottom of the array, because essentially you're going to have a whole array's worth of water now spilling down on one shingle. And so now what I do with my designs is try and start them so that the rainwater runoff is going to slide off the modules and hit the gutter, rather than stopping the array closer towards the bottom of the roof. At the same time, I install in areas where there's more rain and snow doesn't really exist. In an area of heavy snow, it's kind of the opposite, where you want to defer to the top of the rooftop and really have the modules go all the way from the top of the roof down to the bottom, because you want that snow weight to be evenly distributed. You don't want it to mound at the bottom. You also don't want it to mound at the top. So rainwater and structural issues probably don't get enough attention in the industry. And so we kind of, now this home doesn't have a gutter. What I've seen them do in utility scale solar farms is run a strip of gravel right where the water is going to be running off underneath the panels to kind of prevent erosion around the ground mount. I always try and go for aesthetically pleasing designs because that's part of the long-term value. Now, when I select my railing, I select my rail with a U channel. So a lot of rail will be, they kind of just have a very thin little thing here for a nut to slide in. And that is more rigid than having this big open U. What happens with the racking system that I like, a little nut gets put in across this span, and that gives the racking more rigidity after the clamp is put into it, but not before. And the reason why I like this U shape is because I can lay in my cables into the rail and use my rail itself as a cable management system. Otherwise, all these extra cable whips that are coming off the modules and being plugged into the modules and going from the modules to these optimizer boxes are just going to be hanging out underneath the solar array. And you get little cable management clips that can hang off the side of the rail to give you a little bit of a raceway for your cable to go in. I like this U channel because it gives it physical protection from squirrels and also vanishes the cable from sight. And so what I actually do now in my installs is build my solar rails down on the ground and mount my little module level optimizer boxes to the rail. And then I'll tie wrap the cable into the rail and zip tie it. And that's as opposed to using these little metal clips that kind of hang off the side of the rail. And then, of course, the problem with zip ties is over 25 years, the zip ties can dry out and crack too. And so in my kind of system, I'm using zip ties or tie wraps to position the cable into this U channel. But then my module clips come in, and there's a clip that goes between each module along the rail to secure the module into the rail. And because I already have my cable inside that rail, the module clip secures the cable into the rail, so there's no way that the cable can come out. And so rather than using a tie wrap or a cable clip, I've physically secured all but the very last little whip into the rail, and then my cable is hidden inside the rail all the way across. And then I started installing this way, and I thought, the problem is when I mount my module onto the rail, then I have to kind of, as I'm mounting the module, I have to reach underneath the panel and snap these connectors together, and that's a two-person job at the very least. And so what I started to do is say, well, why can't I just put this DC optimizer box just a little bit over and cover it up with the next adjacent module? So I call this hopscotching, and I came up with it. I don't know of any other installers who do that other than the ones that I've told about it, and they seem to love it too, especially with the Solar Edge system. And you just put your optimizer right next to it, and so then you mount the module completely, secure your clips to the rack, and then reach underneath and plug it in, but you're not like juggling the module and the optimizer at the same time. You can mount the module, get it nice and square, plug it in, and then proceed with the next solar array, doing it all along the rail. And so if you're using these module level panel electronics, which are quite popular, you'll plug into the optimizer, and then you'll plug into the optimizer. Your module frame will secure the wire into this rail, and then at the tail end of the process, the very last module on the row, gets two optimizers underneath it, one for its next door neighbor and the other plugged in kind of traditionally. And so for the most part, your cable is tucked away inside of your railing, and then we go into a transition box into the house for an internal conduit run through the rooftop. I don't like putting my conduit across the roof for a number of reasons. The number one is temperature. You're putting copper cable inside of aluminum conduit and then putting it into the most extreme temperature on the roof. You know, that process, even though there's now better safety provisions built into the systems that didn't exist back in 2008, but that copper inside aluminum conduit burnt down a few buildings for commercial projects because the conduit got long enough without putting in any expansion joints, and so it would the systems would literally pull apart, and then the frayed conduit would start biting into the solar cable, and then the solar cable combined with a lack of arc fault protections and or ground whatever. There used to be a blind spot in inverter ground fault protections for multi-circuit arrays. And so when the conduit would pull apart, it would bite into the wire, and then the wire would start ground faulting. And in this, if all the planets aligned correctly, the building would burn down. It's like now there's a limit of about, I think it's 120 feet. You got to put in an expansion joint. So that typically will not apply to most residential systems. And so what I think is a good sign of an installer is if you look underneath the array, being able to see all the way through and not have a messy cabling system underneath. There's another kind of racking configuration that I see high-end installers using, which is a shared rail. And the main advantage of the shared rail, which runs along the edge of the module rather than being in a portrait orientation where the rail kind of runs and you clip in here. Now the modules are in a landscape orientation, and you put your clips like this. And some people prefer the landscape look to the portrait look. I actually ended up using this shared rail system for another reason. The reason is when your modules are clipped in like that, you only get 4 points of connection between the module frame and the rail. On a shared rail system, it's that entire module frame, the whole side of it is laying on top of the rail. And so you get a lot more rigidity out of the system. We're going to talk about that later. When you're installing solar, one of the first things you do is get up on the rooftop and identify where the rafters are. The best way to identify where the rafters are is to use a $1,000 scanner, a $1,000 stud finder to identify where they are. And it's tricky. You gotta, the shingles are not flat surfaces, so you have to slide a piece of thick construction paper underneath the shingle to give yourself a flat surface. So even using the $1,000 way, it doesn't work out well. So most installers will just hammer the rooftop and do it by sound. And, that's good for being practiced to be able to identify rafters with a hammer. Well, then what happens is you get a pretty good guess of where that rafter is, and you drill a hole. Hopefully you hit the rafter. If you don't hit the rafter, you stick a wire down the hole and give it a twist and see how far away you missed it from. And then you take caulk and you goop up that hole, and then it gets covered up with your flashing. So most installers are going to be poking a couple of holes in your roof that won't get lag bolts screwed into them. And so what I do is start out and I just go in and try and identify all the rafters going across the rooftop. Then you can measure it to see if your markings are regular based on the rafter spacing you've measured inside the attic, and that can guide you on if you're off or not. And then you pop down chalk lines to determine where those rafters go and identify where your feet are, and then screw a lag screw into that beam. So chalk line, a hammer, a drill with a small bit for pilot holes, and then a wire to stick down in the pilot hole and then give it a turn to see where the rafter is kind of the standard practice. I like corrugated metal rooftops. I don't see the point of buying a more expensive standing seam roof if you're just going to cover it up with solar. So it's like you're buying an expensive roof and then putting an expensive solar array on top. I would rather go with a cheap roof and then cover it all up with solar than an expensive roof and solar on top. But generally, clients buying solar go for a higher end, and so they end up getting the standing seams. On a rolled metal where you don't have a standing seam, you just screw into the purlin or the rafter with a normal metal roofing screw that has a neoprene flashed washer. And the systems have flashing and sealant built into the bottom. You can kind of see it right here. That makes a good connection. And I even found conduit supports that have the same kind of attachment. This is the S5 manufacturer. So these conduit supports were kind of neat. The only thing I don't like about this picture is kind of how messy this flex conduit looks. Get that up off of the rooftop with these conduit supports. So then we get to standing seam, and kind of the number one mistake I see is installers go with that 4-foot spacing that they're used to with positive penetrations, and they apply it to standing seam, whereas really a standing seam rooftop, you want to go with a railless system where there's no rail underneath the module. That gets the panels closer to the roof line so they catch less wind underneath the rooftop. And then you have a clipping system. And then the problem is you really want to, and maybe, because these clips aren't cheap, maybe when you get into the interior of the roof, you can kind of take it easy with a scant number of clips. Maybe do every other like that. But particularly around the array perimeter, and if you open up the standing seam racking guidelines, it'll say go into every single seam with your mounting clip. And the reason is, if you start eliminating these clips, you take out that whole middle row. Now, all of a sudden, if you're just going down the edges, you're putting all the load into these two metal panels and not the middle metal panel. And the standing seam roofing systems, the way that these metal panels are clipped to the decking underneath, it's not strong enough for that. And so you want to distribute the load as evenly as possible across those clips. You don't have to worry about that when you're lagging into the rafter through the roof, but if you're just kind of sticking the array on top of the roof and not doing anything but clipping it, you need to be more concerned about how the existing roof is attached to the rafter, since you're not yourself positively attaching to the rafter. For Spanish tile, it used to be that you would get these little hooks that would go underneath the Spanish tile. And so you'd have a hook that would kind of have a plate here, and it would come out and then up, and then you'd mount your solar array to the little mounting bracket. You know, that's kind of been retired, and now the proper design is to go with a racking company that has a tile flashing plate that will take the place of a Spanish tile on the rooftop, and they come in various shapes or sizes. For making that roof penetration, and I am a big fan of going into the attic with the conduit. It looks better. There's fewer exposed penetrations. I mean, when you have to support that conduit as it runs across the roof, so you're poking holes in the roof. I'd rather poke a hole in the roof that's covered up by the solar array and not be subject to so much rain. But you get specialty boxes that are made, and this is the big one. I'll use a specialty solar box because it's only a couple of inches tall, so that I can hide it underneath the solar array. Whereas if you do something that's a little bit more generic, like what you can find at a hardware store, the height of this box from the top of the roof won't fit underneath the array. And I like fitting it underneath the array because it looks better. So this is a specialty junction box, and you can see the flashing is built into it. Now, solar's not the only thing that pokes a hole in the roof. You don't need to be concerned about the holes that solar puts in the roof if it's done in a workmanlike manner. So I will use a metal cable called MC cable, and I buy it with the cable already inside. You can make your own out of flexible metal conduit. It's just kind of a pain to pull the cable through this MC cable. And so for my internal conduit runs, I go into the attic, and then I have this flexible cable that I just stick into the box and then take all the way down and come out the soffit and put the inverter on the side, or just come on down into my battery room. Now you have to remember that for the metal conduit in your battery room, it's the best practice is to use the metal conduit with a plastic coating or painted conduit because of that corrosive gas. But often I'll put and this metal flexible conduit, it is rated for outdoor conditions, just not wet conditions. So if you're under a covered awning, having a couple feet of flexible metal conduit is not going to be the end of the world. It's just some authorities who have jurisdiction are going to require, usually if they don't allow flexible metal conduit, they also don't allow EMT, and they're going to require rigid or intermediary conduit. And so kind of the best way to go about doing your install in a code compliant manner for an internal conduit run is to go with flexible conduit through the house, because that flexible conduit is very easy to drop down a wall or string up through an attic. But But then when you get to the roof, you could either transition into a short stub of EMT and then go into your box, or this is the other thing you can't find at a hardware store. You can connect right when you come out of the rooftop, you can connect a multi-hole connector and transition into your rooftop PV cable at that point. So again, I like hiding that transition underneath the array. So a lot of this stuff now we do down on the ground with pre-assembly so that it makes the install just go much faster. Anything you can do on the ground, any kind of pre-work you can do as far as, pulling your cable through the conduit before you get up into the attic, which is something you can only do with flexible conduit. Generally, that's going to get your costs down, and often it'll improve the quality of your work too, because you're not doing it on a hot, slanted surface. So here we are on doing some ground mounts, and I've run into a few ground mounts where the logistics of getting concrete out to the site is difficult, and certainly that will apply to a number of off-grid sites. But we do have a Bobcat on site. So I recently started to look into ground screws and earth screws. And they went in pretty well. You have to hand guide them because they want to kind of turn out of place when they get when they're initially going in, they kind of want to jump out of position. You kind of have to hand guide them into place. You use a ground screw for rocky terrain and an earth screw for more like sandy and clayey soils. And that can eliminate the necessity of concrete on the system. So they are a little bit more expensive. You're not going to save any money compared to augering out a hole and pouring in concrete. It comes out to be about the same. But you do save on the logistics of the concrete, and some people think concrete's bad for the environment, so doing solar, it's worth thinking about. Now for ground mounts, kind of the popular style is, I call it scaffold style or bleacher style, where you have 2 rows of posts and then some cross bracing in between them. I think that style, there's 2 reasons why I don't like it. One, I'm not a big fan of just giant solar arrays in terms of aesthetics. I think they're kind of like giant satellite dishes where the owners and the installers are really enthusiastic, but they won't really stand the test of time. I also think that the bleacher style makes maintaining the ground underneath it kind of a hassle because you can't really mow underneath the array or even walk or access underneath the array very easily. But they're pretty simple. You can either use concrete or just screw into the ground. We were able to use these things and get them pretty level using just general contractor laser finders, laser levels. But if you're doing it yourself and you only have a limited budget, you don't have a laser level, you can cut off the top of them. So they do go into uneven ground, all right. Utility style racking, instead of having bleacher style, you just have 1 row of posts, and these are generally pile driven into the ground. A little bit easier to do your earthwork when it's 1 single row of posts. Now that said, because it's only 1 post or 1 row of posts instead of 2, the foundations go substantially deeper. Well, that's not completely true. It goes substantially deeper if you have two panels stacked. If you just had one panel stacked, you wouldn't need as deep of a foundation. And so then you get into utility scale single axis tracking, and it's only one panel, and so the posts don't go quite as deep as something that you would get with pile driven. And I really like this style because A, it's very easy to get underneath the array and do your dirt work. B, the panels are this when it's perfectly flat, they're at about waist height, and so you can kind of see over the top of them, so they don't visually obstruct anything. And also, it kind of makes like a fence that lines the road or property line. And so there's a lot of properties where if you buy 40 acres of land, you might not have a fence between your line and your neighbor, and putting in a solar array right there, that's a permanent structure that's going to define your property line. For that matter, you could put, fence netting between these single row posts and actually make it a fence. Utility scale, you might have looked at on the last picture and said, well, is that really one module or two? Because that thing's super tall. Utility scale modules are about 20% taller than residential. They're just so tall, it's hard to handle up on a rooftop. But one thing that's nice about that extra length is these cable whips are designed to go into portrait or landscape. And with the taller modules, that extra 20% gives you a little bit more cable width. So what they do on single axis tractors at the utility scale is, instead of plugging the modules into their next door neighbor, they go every other module, and then that allows you to come back home. So your circuit starts and stops in the same place, and that's twofold. One, you don't have to make this home run circuit that you do in residential. And two, all of this extra unused cable is voltage drop. So you get a little bit of an efficiency boost by doing this kind of wiring technique. Now, another issue to think about is, often with off-grid, your home will be in the forest and it'll be surrounded by trees. And so you might have, I just did one where there's a field off to the side of the neighbor's property, but the cabin is in the middle of the forest. We couldn't do a 150 volt circuit over a long distance because of voltage drop. The longer you go, the more efficiency is going to come off of that. And if you start at 150 volts and you go a long distance, you might end at 100 volts, and that's not enough to get your charge controller to work efficiently. On top of that, with a whole bunch of multiple circuits going home, you're going to get killed on your cable cost. I mean, generally speaking, when you're talking about cable, you got the thickness of the cable, and then you have the jacket of the cable. It's like a water balloon, where the inside of the water balloon is amperage, and the outside of the water balloon, the plastic, is the voltage rating. And so, there to some extent, when you are upsizing cable because of voltage drop, you're buying a lot more copper than you really need. You want to kind of right size it so that a lot of cable will be rated for 600 volts or 2000 volts. Solar cable is rated for 2000 volts, and there's hardly even 2000 volt capable products out there. What really drives up the cost of cable is not the jacket so much, but the copper inside. remember, power equals volts times amps. Amps is more closely related to the copper inside. Volts is more related to the jacket rating. You know, it's not so linear a relationship, but generally speaking. And so what that means with power equals volts times amps, if we have a very long distance to go, what we want to do is increase our voltage and decrease our amperage. And that's why I like 600 volt charge controllers, is because I can take that 600 volts back from the array and locate my charge controller at the house. Or if it's a 3-story building, you know, the solar arrays on the roof, the charge controllers in the basement, you know, even that distance from the roof to the basement, it's better to do in higher voltages. I guess this is kind of out of order. The thing about utility scale is 10 years ago, tracking did not exist in the utility scale market, aside from a couple pilot projects, but nothing, you know, there weren't many manufacturers making tracking systems for the market. But there's something special about single axis tracking, and that you're kind of using the module frame structurally in a way that when you're building bleachers underneath the array, you're not. In that the module does have some cantilever ability, and so now we're putting that to use. And so single axis tracking is like, okay, well, we're only doing one row of modules, so we don't need very deep foundations. We're making better use of our module frame. And so the added cost is, you know, whether you're going 2 modules deep and having a second row of piles, or 1 module deep and having 1 row of pile, you're paying for those piles either way. Whether you have 1 big thick cross beam or 2 smaller cross beams, you're paying for that cross beam either way. Whether you have 1 big clip that goes at the middle of the module or 2 small clips that go along the edge of the module, you're paying for the clip either way. And so really the only added cost of going from a fixed array to a tracking array is the cost of this flexible bearing that sits on top of the post, as well as an actuator needed to move the array up or down. And so for that reason, single axis tracking at the utility scale has only increased the cost of projects by about 5%, and the gain from that is about 15%, and you can calculate that in PV watts, as we talked about yesterday. And so single axis tracking, as opposed to double axis tracking, which has more foundational costs, or fixed in place arrays, single axis tracking has gone from non-existent to dominant in the utility scale market. But it's almost non-existent at the residential level. Well, why is that? Well, a lot of solar installers will tell you, oh, whatever money you'll spend on tracking, just use it to buy more solar panels. Well, okay. But if I buy more solar panels, add another panel onto this, I have to add a whole new foundation onto it. I'm not just buying the panel, I'm buying the racking and the charge controller capacity and the labor involved and all that. No, the reason why we don't see single axis tracking for residential ground mounts is because there's no manufacturers supporting that market. You know, manufacturers would rather sell, you know, a system 10,000 times the size to one client than, you know, a smaller system to 10,000 clients. Well, then again, there are some residential tracking companies selling double axis trackers that are quite large, and I think they look like satellite dishes. When I price them out, it's not like utility scale where you get a 5% cost increase for a 15% performance. It's more like a 50% price increase for a 15% performance. But again, I believe that's because the single axis tracker companies are selling to a luxury market. They're not really honed in on cost effective design like you would be at the utility scale. Now, the thing is, do you need the extra energy when you track? Maybe, maybe not. If with a fixed array you're already getting up to the top of your battery, the increased production is just going to result in more stranded electricity. Then again, I came across a job site where here's the array location, and on the south side of the array is trees, and on the west side of the array is trees. On the north side of the array is trees, and there's really only a clear view on the east side of the array. Now, in the summertime, the sun is more up than south, and so having an array that could face east in the morning to get this extra production and then kind of turn to face north and capture the additional production in the midday would be a pretty good fit. This is commenting on the stranded electricity. And so if you do tracking, maybe your battery gets full earlier. Maybe you have a little bit more electricity in the morning. But it's not to say that you have to have tracking to live off grid. So, what I'm saying is the performance increase of tracking for residential off grid may be a little bit overstated. But on the other hand, the utility scale market thinks it's cost effective. Additional morning and evening production means less load on your battery, or even in a north-south orientation, you would get more production in the winter as well as in the summer, and we saw that that's when our battery is most strained. Now, whether you get more production in the winter and summer because you're doing east-west tracking versus north-south tracking, it doesn't really matter. Either way, or even if the tracker was in a northwest or a southeast orientation, being able to track over one axis is still going to result in boosted production no matter how you cut it. And so we went and built one to kind of demonstrate that yes, indeed, it's possible to do residential single axis tracking. This was the prototype. We used helical piles going in. This was the one that we didn't hand guide, so you could kind of see it went in a little crooked. The others were much more straight. These bearing blocks only cost $30 a piece. And so we had 14 piles on a 7 kilowatt array. And so it only cost us, an additional $300 in parts to make the array manually adjustable, which is a good place to stop. Let's see, did I post? the finished one there. Let's see. Sorry, we just built this like 2 weeks ago, so I didn't put it into the presentation. So here's our residential single axis tracker with our $30 hinges. We actually went and used a shared rail residential racking system because we couldn't find those more robust mid clips. And so the module frame is supported all across this area, and there's a shared rail racking going on there. And so you look at the cost of the bearings, less than $300, and then the cost of the control board and the actuator, less than $1,000. This was a $30,000 residential off-grid project. So for about $2,000, or a 7% increase in the cost of the project, now the client gets to be able to face east in the morning to capture this eastward view, and then also in the afternoon when the sun is more up than south, he also gets that added production. And so at least in my experience, it's not that tracking is only worth it at the utility scale level due to economies of scale. It's that those same economies of scale mean that the utility scale tracking companies do not target the residential market. And because all these companies used to be residential racking companies, but they went into utility scale and then developed their designs, they've never come back home to the residential market, and it's just sitting there in a vacuum, maybe because it's so small at this time. But, using some good old engineering know-how, we were able to develop a utility, a residential single axis tracker based on the utility scale form factor. And at least in our experience, it seemed to boost the project economics and be cost effective. And so here's some of those parts if you're interested in learning more about that. People say, well, I don't like the idea of tracking because it means more maintenance. Well, it doesn't mean that if the tracker stops tracking correctly, it'll still produce power. Like the late Mitch Hedberg said, I like escalators because when they break, they become stairs. Sorry for the convenience. It's the same thing with the tracker. A broken tracker is still going to produce power while it's being fixed. But at the very least, I would say look towards the single row of piles, making that manually adjustable, particularly for off-gridders, so that you can adjust your array and boost that wintertime performance when you need it. All right, generators. I really only have kind of one thing to talk about with generators. This kind of surprised me. Generac is now selling a generator that's marketed as made for alternative energy systems. And so you would think that that is the generator you would want for your residential solar array. Well, That's not the whole story. First is most of your battery inverters will have a generator control board to trigger an auto start. And so you don't need a generator that has its own let's monitor the battery voltage and when it gets low, start up the generator function, because it would be better to have the inverter, which is the brains of the system, drive the generator rather than the generator drive the generator. You know, where that came in is these battery these off-grid renewable generators will market themselves as variable speed generators that can supply a load in tandem with solar, so that if your solar array is 3 kilowatts and your load is 6 kilowatts, the generator will spin up to power the load. Well, the problem is, what if I want just to charge my batteries and I don't really have a load from the home? I just want to force power from the generator into the batteries. A generator that is very load sensitive may not want to throttle up to overcharge the batteries during a maintenance cycle. And so to some extent, having a dumb but controlled generator is better than having an intelligent generator that may have its own brain and go off and do something that you don't want it to do, like not overcharge the batteries, which you need to do as part of your battery maintenance. And so we were just out of the box, you know, we can tweak the settings, but right out of the box, our renewable generator was not wanting to equalize our batteries. That's the process of pushing more power into the batteries than they're really capable of, just briefly, in order to kind of clean the battery terminals. It's only something you do with sealed batteries. You don't do it with unsealed batteries. So we don't really need the controller because our inverters already have the controller. You know, really the functions of the off-grid renewable generator are, it has more oil, so you don't need to maintain it as much. It has soundproofing to reduce the noise of the generator, under the understanding that these are generators that you're going to be using frequently rather than like a backup generator for a home, which you're using infrequently. Well, you look at the price of gas compared to the cost of solar and batteries, and you don't want to use your generator every day. Maybe a renewable generator is good when you're living in Alaska and you're going to go through a very dark and long winter. But if you're living in the inner 48, I really don't think you need a renewable generator. I think it would be much better just to have a very basic generator that you can turn on with an auto start. So almost like a portable generator, but not all portable generators have the wire inputs for an auto start to be wired up to it. The renewable generators have variable speed motors that allow them to operate more efficiently at lower speeds, but mainly it's that they can better guarantee a 60 hertz output. A regular generator will use more gas under higher load and less gas under lower load. It may not provide a clean 60 hertz signal for residential electronics to be used under full-time use. And so you get into renewable generators, and it's really that they're designed to be running a home full-time, unlike a backup generator. But a well-designed off-grid system, the generator really should only be used as backup. And so you don't need the full-time generator to do that. And it's not like renewable generators are the only variable speed generators. It's more that as the generator is throttling up and down, it can maintain a 60 hertz signal rather than having more distortion like a entry level generator. So, the short of it is that renewable generators are a higher quality generator. I would rather get a lower quality generator and spend more money on batteries than the other way around. So let's say I'm using a generator to generate electricity. It can work well at the utility scale, but the short of it is that it's very expensive to generate electricity with a residential generator. We're not trying to give our customers a 21 cent a kilowatt hour electric bill when they're currently paying 12 cents a kilowatt hour. What we want to do is just have this generator be used a few times a year. Now, for that matter, that's why I think it would be better to go with a smaller generator rather than a larger generator, simply because it's cheaper. So I'd rather have a 5 kilowatt generator that runs for 10 hours a day on that winter day when I really need it than a 25 kilowatt generator that I only run for 2 hours a day, but it costs 3 times as much money. The point is you're just not using the generator very often. And so back in the model we were looking at yesterday, I will go in and model for my system sizing my generator runtime to say, I don't want my generator to be having to run, every other day in the wintertime unless it absolutely has to. So in this model, I might look at actually increasing the size of my battery bank. If I made it if I made my battery bank, which is currently this large, if I made my battery bank this large instead, then I could probably get rid of running the generator here and running the generator there. And then on top of that, if I click my generator on at this point and charge it all the way back up to the top, I could probably get rid of running my generator here, here, and here as well. And so when I'm kind of right sizing my system, reducing the number of times that the generator needs to be run and getting that down to, 2 or 3 times a year is a pretty good number. Because remember, if you're running your generator every single day in the wintertime, all you're doing is increasing your customer's electric bill and getting them to run off fossil fuel, which is counterintuitive to the off-grid solar lifestyle. And so I'll go in and compare say a 90 kilowatt hour battery bank that would require me running the generator 10 times a year versus 120 kilowatt hours that would require me to run the generator 4 times a year. How much money would that add to my upfront cost versus how much money am I going to be spending on gas for that increased runtime? And all else being equal, that's kind of the hinge in your design optimization for off-grid that'll solve the how large of a solar array do I need and how large of a battery bank do I need. If you can quantify it in terms of, well, what does that mean in terms of generator runtime? you can get into a reasonable, cost-based assessment of what size of battery bank do you need. Peace of mind is also important. If the client has unlimited budget, but he wants his off-grid array because he wants that wilderness paradise, well, maybe he doesn't want to listen to the generator running for 10 hours a day in the wintertime. And so that might be a reason to increase the size of the generator. I would not have the generator be substantially larger than the output capacity of the inverter. And then there's other kinds of generators, like, do you need natural gas, or can I just go and get a generator that I just go to the store and fill up with gasoline? Well, generally speaking, propane and natural gas are going to be cheaper than running your a gasoline generator. But just remember, you're not using it very often, so it may be quite convenient to just have an extra gas tank and have that generator there be on standby when you need it, but to design the system for not actually needing it. Now, in other words, the cost of the fuel begins to matter less and less if you're not reliant upon it. All right, let's keep moving along. What I've done in this section is just included different electrical line diagrams for you to take a look at that might, a couple of different configurations. Here's a complicated one where we have a generator wired into the service panel. We have a grid-tied service panel. We have a critical load panel. We have two inverters being wired into the AC panel as well. And then we have over here our battery bank that's being wired into a DC bus and the positive bus and the negative bus. We see on the positive bus that we have breakers and the negative bus does not. This is because this particular system is a negatively grounded system, so that the negative is connected to ground. If you had a floating system where the negative is not connected to ground, you would have to have breakers on this negative bus as well. Here's our charge controllers landing on breakers that then get wired to our DC bus. And so we see our charge controllers on breakers, our inverter going to the inverter. That's that disconnect switch breaker. And then we have an AC side on top. Multiple charge controllers, one battery bank. So how do you go about designing the wiring diagram for these things that you'll probably have to submit to the permit office? Well, most of your battery inverter manuals will have wire diagrams for their system. These are more wiring diagrams that show you where all the connections go, rather than a more simplified one-line diagram. In solar design, with battery lists, the manufacturers have sizing tools available on their website, and they're pretty simple. You use this module, this inverter, and it tells you how many modules can fit per circuit and how many circuits you can have. So I could do 7 modules, 3 strings of 21, or if I had a 12 module system, I could do 2 strings of 6, all using this particular module and this particular inverter. There are design softwares out there. This is kind of my favorite residential one, which is called Solar Design Tool. And it does a lot of calculations for you, and it does things like wire sizing and conduit sizing. But the problem is all of this stuff is just kind of written for batteryless solar. So all of the commercial software out there is not well written for these, battery-based systems. Now, what Solar Design Tool will do is give you things like conduit sizing, voltage drop, National Electric Code. And so what I'll end up doing is this isn't that important, relevant to class. What I'll end up doing first is just going into my traditional solar design software and designing the wire diagram based in my software, but then ultimately off-grid design, you're exporting it into AutoCAD or DraftSite, which is kind of like a free AutoCAD, and then finishing it out. So I'll go and do my one-line diagram for my solar array, and then I might switch out the inverter block with my 3-circuit charge controller, and then kind of use the, either way, it's still going to be the same voltage and amps coming back to my charge controller, and that's still going to be in the same conduit size. So you do have to be a little bit more masterful to make sure you're not making a mistake. But to make it look good, you're not going to find one software that does it all. So, you're eventually going to have to get to exporting it and finishing off the document in CAD, kind of using the wiring diagrams from the manufacturer as a guide. This is budget items. This is actually from a couple years ago, so I wouldn't put too much stock in it. So now we get into home automation. I was actually on a solar project for a retiree, and she was trying to bid home security and media servers and fiber optic through the house and home automation. And her system, she was really getting contractors bidding her home automation for multi-millionaires, and the contract pricing was coming back being like $80,000, $90,000 plus programming on top of that. And so she came to me and said, well, do you want to figure this out, do it? And I said, yeah. I think there's a lot of overlap between home automation and on-site energy systems. I'd like to do more to combine them together, because home automation or home computer systems and Ethernet systems, they put out a lot of heat, so it would be neat to combine them together. We didn't do that on this project because we just didn't want to bite off more than we could chew. But there's a lot of automation features that battery inverters have that could be interesting to incorporate into home design. So for example, you got state of charge triggers based on high battery voltage, low battery temperature, low battery voltage, high battery temperature, and obviously like high battery temp, low battery temp, well, that's when you'd want to turn on a heater or turn on an air conditioner. Low battery voltage is when you'd want to turn on a generator. High battery voltage is when your battery is charged and your solar array is producing stranded electricity and you don't have anything to do with it. And so the computer nerds might say, well, that's when you Bitcoin mine and convert electricity into money with Bitcoin. Or the architect might say, well, why don't we have a water fountain that only turns on when the home is at a healthy state of energy. And so instead of having to pull up your cell phone or your online monitoring system, you can just glance around the house and determine what the state of charge of your battery is, at least in terms of things being healthy or not healthy. So you get some triggers that are built into your battery inverters that can allow you to send a relay to turn circuits on and off, turn the generator on and off. This is a basic thermostat wiring. I actually kind of learned something interesting about thermostats where they have these batteries here. The battery in your thermostat is a perfect example of a grid-tied battery similar to the Tesla Powerwall, where it's not intended to run your thermostat full time. It is just there to provide a little bit of power if the power goes out. That said, you can get a little in trouble because there are some thermostats that use such little power that they are only powered by batteries and not off of the cables that come in from the back of them. So not all battery-powered thermostats are powered by the wall. And so you go on Twitter and you look for problems with the Nest thermostat, and they're almost uniformly because the homeowner has taken their thermostat that is a battery-only thermostat and replaced it with a Wi-Fi sucking Nest thermostat that really can't be powered by batteries for very long. And so the complaints are, oh, I have to swap my batteries out every week on my Nest thermostat. They're not realizing that these higher end smart devices will often consume a lot more power than the devices they replace. Well, so what we see in this particular thermostat model is that they have additional auxiliary relays that could be used to provide a little bit of energy management with just using the existing resources that you already have on the home. So a good one for an off-grid system would be to trigger via an auxiliary relay an electric heater, like an electric space heater. Even if your home is normally powered by gas, why not turn on an electric space heater when your battery level is at a healthy state of charge? So not just home automating things like music and lights and window blinds, but also the energy consumption of the home. So how do you do that? How do you wire it all together? So there's a term now called a hub, H-U-B, hub. And what it is, it's a computer for a couple of devices. And some home automation products do not need a hub. They'll say, oh, it's all done over Wi-Fi. And I would caution you away from those Wi-Fi only devices that don't have hubs, because even though they work out of the box and it's very easy to download an app and use them, if they can't talk to the other devices in your home, then you're always going to have this manual process of control and not be able to automate it. And so there's a home automation platform put out by Google called Home Assistant. And you can run it off a $35 computer called Raspberry Pi, but you don't have to. But it's all based around smart home platform, whether they be Wi-Fi or the various other platforms. Now, is Wi-Fi the best platform? And I would say for home automation. And I would say no. Wi-Fi is high energy, short range. Home automation does not need high energy. With Wi-Fi, you can broadcast 4K internet video over it. If I'm just trying to trigger a relay, I don't need a torrential rain of data to do that with. That takes energy. Energy uses our batteries. And so the other platforms are called Zigbee. And then another one is called Z-Wave. And that's kind of my preferred one. And so you get a lot of home automation companies just making, this is a USB stick to add a Z-Wave antenna to a Raspberry Pi so that it now can communicate on the Z-Wave platform. You know what all this stuff is? The Z-Wave or Zigbee, as compared to your remote-controlled cars. Remote-controlled cars are even done on even lower frequency ranges with longer range and less energy. The signal quality gets to be a little bit tough when you get too low energy, because that's where you can click a button and it turns on two different devices. It's not good at attenuating the signal. Remember when you had a corded telephone in your house, but it was a wireless phone base? So instead of having the phone hardwired in the wall, you could pick the phone up off the wall and talk to it. And if you're still with me now, remember again when there was a next step in corded phone technology where you no longer had to be 40 feet from the phone base, but you could be 100 feet from the phone base or even more, like a longer range wireless phone for your house. The first generation wireless phone was done on that 450 megahertz signal, the same thing like a RC remote controlled car. All of this Z-Wave, Zigbee stuff is done on around a 900 hertz signal, which is like that second generation cordless phone technology. It just goes a little bit further, a little bit better signal quality, but not the same amount of energy usage as Wi-Fi. And so whether it be Zigbee or Z-Wave or whatever, Home Assistant is the glue that can mash all of these products together as long as they're compatible. And so we have a wide variety of Z-Wave products. Here is a 40 amp breaker that's a Z-Wave technology, so that you could have a 40 amp device that you could be turning on and off. The thermostat that we just looked at could be a Z-Wave thermostat, so that these auxiliary relays could be used not to be triggered over hardwire, but to be triggered over the Z-Wave platform. And so you could combine the two to turn on and off floor space heaters. This is a Z-Wave energy monitor that clicks around the cords in your electric service panel so that you can monitor the energy that flows through those cords. So, where we're at now is saying, you know what, your solar monitoring systems will tell you how much production is coming out of the array, but they won't tell you how much consumption is required by your home. And so I have a customer in the TVA grid who's like, well, I want to know when I'm outflowing onto the grid because I get paid less for my outflow than I do for my inflow. Well, his solar monitoring system doesn't tell him that. It just says your solar array is working. So instead of selling the solar monitors, we put in these service panel monitors so that he can actually see his inflow and his outflow. These are remote controlled outlets that cost $5 a piece, and normally you would be controlling them with a little rink-a-dink control to click them on and off. The Home Assistant platform is possible to take a RC computer chip, wire it up to the Raspberry Pi, and start turning these breakers on and off. Now that's a little bit more hacky than your standard fare, and that's why instead of buying a $5 intelligent smart plug, people opt for the $40 Wi-Fi smart plugs. But it's a little hard to do that throughout your entire house when the costs are so expensive. And so now it's possible to do like a Z-Wave thermostat with a Z-Wave hub. And if you're not into Raspberry Pi and programming your own computers, like one very popular option is Samsung Smart Things, which is instead of a Raspberry Pi hub, you get the Samsung's Smart Thing hub. So for that heavy-duty deep freeze, instead of putting it on a timer, you have it turn on whenever you're outflowing onto the grid or whenever your battery is on a healthy state of charge, and have it freeze food with your surplus electricity and then coast when, at night instead of drawing load off your battery bank. Solar water heating, that's another big application. Is could you just, there's a product out there where the solar panels are directly wired into the water tank, or you could have an intelligent water tank that uses the surplus energy of the entire system, which is a better way to go about it. So then we get to kind of where I think, hey, all this stuff is great, but it's still very expensive. So can you build a little bit at a time? A lot of customers have batteryless solar. So how can we not scrap the entire system that's already there, but enable it to go off grid? And what I'm showing in these slides is that not all solar manufacturers want you to take their systems off grid. So they say, look, if you're putting a generator on the system and your solar edge inverter on the system, they better be interlocked and separated from each other. Otherwise, we're going to void your warranty. Now, that doesn't mean that a generator can't work with a solar edge system. It means you're going to lose your warranty. Here's the Schneider inverter that says, no, we are able to couple them. This is a warning that says this is a battery inverter, and it says don't add our battery inverter to a solar array that doesn't have batteries unless that solar array is able to stop production if the battery bank is full. Now, actually, what the battery inverters do, the higher end ones, is they will shift the frequency of their electrical output and trick the grid-tied inverters into turning off. So when there's a power failure, the frequency of the grid changes. And so your higher end battery inverters will change the frequency of your home from 60 hertz to 59 hertz, and it'll click the batteryless solar arrays off. We just have time to get into the main points. We were talking about this yesterday, how resistive loads like heating loads are actually very good for battery banks. It's the compressor loads that are hard. The only issue with resistive loads is they use a lot of energy. So it's not that they're hard on the battery bank. The motor loads are much harder. So this is the Franken solar kind of design, where let's assume you already have a solar array with an inverter. Or maybe you want to go with a solar array and the solar edge system that has the lithium ion battery pack. And that's going to be a grid connected array that sells back to the grid. And then your battery pack is going to be able to protect some critical loads. Okay. But still, most solar customers want to have whole house power during a blackout, even if they remain grid connected. And so you could go and get a cheaper off-grid battery inverter that's not designed to backfeed onto the grid, and then land it at the top of the bus bar on a generator interlock. And that way, if the grid goes out, you can flick on that generator interlock, turn on your lead acid battery bank with your larger lead acid battery bank and battery inverter, and then trick your batteryless solar array into turning on. Well, the question is, how do you charge these batteries? And that's where, you just take your solar array and wire up a charge controller to charge the battery bank. Now, the question is, if you already have a DC bus coming down from the rooftop, can you share it between two inverters? The answer is yes. But the battery and the inverter companies will void your warranties if you do. But technically, you can. Now, I've talked with them, and I say, well, what's the concern here? And the concern is that by tapping an additional charge controller onto that bus, that not enough power makes it to the inverter so that the charge controller ramps up and sucks the power out of the line, and then the inverter turns off. And so they don't want you to do that because of quality, but actually what it means is all you need to make sure is that you have enough power on the system to work it so that you have enough panels. So like a short circuit of panels would turn the inverter off, but a long circuit of panels would just act like it was an overcast day as far as the inverter is concerned. And then this charge controller, as soon as the battery bank was filled up, it would go away and all the power would keep going through the regular inverter. Now, another concept is, okay, lead acid is cheap, but lithium ion is better for, say, a tankless water heater, for something that's more dynamic, a burst mode, or responsive. Now, this 12 kilowatt inverter has a burst mode rating of 36 kilowatts for about 30 seconds. So it could still do surge loads, compressor loads, motor loads, things like that. But what if you go and buy a batteryless solar with a lithium-ion battery bank, and then you want to convert to off-grid later? Well, these lithium-ion battery inverters have demand management loads so that instead of feeding into the grid, they just monitor through CT rings the load of the house and only turn on when the load spikes. And so actually, you could put a generator interlock panel here and then use your battery inverter to power the house, and then just reprogram your lithium-ion battery to do demand management so that you reduce the spiky loads from your battery bank. And so there's actually room for lithium-ion and lead acid to exist feeding the same system, using lithium-ion for a small lithium-ion battery bank for demand management, and then lead acid for base load. And then why would that make sense? Well, you still get the lithium-ion battery backing up the critical load. And so now I have a solar array charging my battery inverter, but also able to charge my critical loads so that if my battery inverter fails, I still have some backup power capability. In other words, furthermore, you can wire it so that your grid-tied inverter can backfeed to the grid, and your off-grid inverter is just hanging out being used as backup. And then when you're ready to do a full-blown conversion, get rid of the grid, plug in a generator, and then switch into off-grid mode. And an elegant part of this system is that you can still use today the expensive grid-tied lithium-ion inverter backfeeding to the grid. And then if your grid policy changes and you want to do an off-grid conversion, that's when you would add the cheaper, not made for grid connection battery inverter with your flooded lead acid battery bank. And you achieve an element of double redundancy without just simply buying two of everything involved. So, each part plays its own unique role when it's healthy, but the system could fail elegantly by having an inverter that's specific for lead acid, an inverter that's specific for lithium ion, and then the proper switch gear to make it all work. So that's kind of what these next slides kind of go through, which is basically saying that, hey, even though the inverter manufacturers tell you, no, this does not work, indeed, you can combine multiple battery chemistries together on the same circuit. What you want to avoid is having two master inverters trying to drive the system, but then again, your lead acid battery inverter can be the master with your lithium ion enabling the demand management mode of the lithium ion inverter. The concept of that is called an energy server, and that's more of a commercial thing that we explore further in our commercial demand management class. So I'm just going to kind of quickly get through the rest of these slides. Basically saying as long as you stay within the operating parameters of the voltage requirements of the system, there's a minimum number of minimum amount of voltage the system needs to work, a maximum amount of voltage that the system needs to work, and anything in between is power that you can draw off of the DC bus into your lead acid charge controller, provided that you have a 600 volt DC home run for your solar edge system and you're using a 600 volt charge controller. It will work. It's just that Solar Edge won't like you very much because they want to sell you the whole system. So that's, I kind of gave you the short version of it, and then this kind of walks through what we just discussed previously. You've probably been waiting for this slide. Here's different costs of different system materials. A good budget for a completely off-grid residential home is between $80,000 and $100,000. So it's still expensive. That's the reason why you would build it out in stages based on what your grid policy is.
JR,
So with that, we're at the end of the program. I'm going to pass it back to Tim.
Okay, great. Thanks, JR. Thanks, everybody in attendance. When I close things down, everybody will be sent over to that brief quiz that I mentioned earlier. Again, it's not meant to catch anybody up. It's just meant to prove attendance. In the event that you have any problems with it, just call into our office or email us, and we can help you out with that as well. Just a little heads up, it might be a little hard to reach us immediately following the webinar. We're currently experiencing our third blizzard for the last couple days, and we are closing the office early. So we will have customer service here, but if you have trouble getting a hold of anybody, just bear with us as we try to recover from the horrible weather we've been having these last couple weeks. If your certificates, they take about 5 to 7 business days to get to you, barring that we do have a quiz returned from you. If you need them any sooner for licensing purposes, again, right back to those emails or call into our office. We can help you out there as well. But again, thanks everybody. Thanks, JR, and everybody have a good day.